Okay, here goes an explanation of position, velocity, acceleration graphs. This is the one that we had on the quiz. And it was obviously pretty difficult. So we're given a position versus time graph, and we're supposed to come up with the velocity and the corresponding acceleration graphs. So what I've done down below is tried to describe that motion. So when describing the motion, think about one, is it moving? So I'm going to write a couple things. So first of all, is it moving? And then if it is moving in the positive or negative direction? And then, is it speeding up? Okay, so it can be going at a constant velocity. It can be speeding up, and I'm just abbreviating here, sorry, or it can be speeding down, so slowing down. Okay, so keeping that in mind, what did I write? I wrote that for the first section it was a constant positive velocity. So constant velocity meaning it's not speeding up or slowing down, and positive meaning it was moving in the positive direction. For the second section, I said it's not moving. Third, it's a constant negative velocity. And then for the fourth section, it still has a negative velocity, but it is slowing down. And then lastly, it has a positive velocity and it is slowing down. So let's take a look at that and see if it makes any sense. In the first section, well, let me back up. When going from position time graph to a velocity time graph, all you're paying attention to is the slope of this graph. Okay? It doesn't matter how high up it is. It doesn't matter how far down it is. It doesn't matter if it's crossing the time axis at all. You're only looking at the slope. Okay? So the rate of change of position with respect to time is velocity. We just pay attention to the slope. So this line could have been up here. It could have been down here. It could have been here. And it would be the exact same thing. All right. Let me back. Oh, I am not able to erase. Oh well. So we look at this. It's a straight line, meaning it has a constant slope. So the velocity is constant. It has a positive slope, so we know it is a constant positive velocity. So what I wrote is constant positive velocity. So all we know about the velocity time graph is that it is constant, meaning it's going to be flat or horizontal. Imagine the value here is something like 2 meters per second. Okay, it's constant, meaning it stays at 2. It doesn't move up or down. So we have some constant positive velocity. That line could have been drawn here, could have been drawn here, could have been drawn here, could have been drawn here. All of those would be correct. For the second section, looking at the position time graph, you note that the position does not change. If something's position does not change as time goes on, it means it is not moving. The slope as well of this line is 0, so we know the velocity is 0. And the slope stays at 0, so we know the velocity stays at 0. For the third section, this is a straight line, and it kind of looks like it curves, but really I used a ruler to draw that. So this is a straight line, and it has a negative slope. Okay, so straight line means constant slope, means constant velocity, and it has a negative slope, meaning constant negative velocity. So because it's a constant velocity, it should be flat. Because it is a negative velocity, it means it should be below the time axis. Anywhere down here, a nice flat line would be perfect. Up here, no. So again, we're not looking at whether this crosses the time. We don't care about whether that crosses the time axis. A lot of people get confused by that. They see, oh, it's going down, so the velocity must be going down. We look at the slope. The slope is negative. the slope is constant, so the velocity is negative and constant. Okay. So when the position time graph, time graph is curved, all of a sudden we have a slope that is changing, so we're going to have a velocity that changes. So yeah, this velocity is getting closer to 0, this velocity is getting closer to 0. So once this position time graph is curved, then we're going to have a velocity time graph that has some slant or some slope. Notice how when the position time graph is straight, the velocity time graph is flat, is horizontal. That is always the case. So for this fourth section, we have some negative slope, okay, and it's still a negative slope, and it's still a negative slope, and it's still a negative slope. But notice how it is flattening out, meaning the slope is getting closer to 0. So we have a velocity that is negative and is getting closer to 0. Our slope is negative and getting closer to 0. So our velocity is negative, meaning below the time axis, and is getting closer to 0. If you had drawn that, well, let me back up. Okay, so we have a negative velocity, and it is getting closer to 0. Notice, and this is sort of this is a detail that is important. Notice how as we transition from this region to this region, the slope here is constant through that little region. It's not a situation like this where there is some radical change in slope. Okay, so like that would be a radical change in slope. This would be a radical change in slope. But that, so right around here, that would not be a radical change in slope. It's constant kind of through the transition. So because we have a constant change, or the slope is basically constant through this transition, notice how the velocity remains constant through here. These graphs are not separated like that. If they were separated, it would mean there would be some radical change in velocity, which would mean some radical change in slope. For example, over here, radical change in slope, so there's this break in the velocity time graph. In reality, it would be a very great acceleration. So this is like a golf ball being hit by a club, or running into a wall or something where your velocity changes rapidly. Okay. Lastly, so for our last section, all of a sudden, again, we don't care whether it's above or below the time axis. We're just looking at the slope. Notice how the slope is positive and steep. It has some great positive velocity, and it has a great positive slope. Positive slope, positive slope, positive slope, positive slope, positive slope, positive slope, positive slope. Yet it is flattening out, meaning the slope is approaching 0. So we have a positive slope that is approaching 0, meaning for this we have a positive velocity that is approaching 0. So the positive velocity means it's above the time axis, and it is approaching 0, meaning it starts from somewhere up here and slopes downward. So if we had drawn that like this, or like this, or like this, all of those would be correct. Okay, lastly, going from the velocity time graph to the acceleration time graph in general is easiest for people. We have flat, 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 so 0 slope, 0 slope, 0 slope. And then we have some positive slope, so it is some positive, so constant positive slope, constant positive value, and then we have constant negative slope, and so constant negative value. Let me give you a couple generalizations. This should help. If the position time graph is straight lines, the velocity time graph will be flat or horizontal. If the position time graph is curved, the velocity time graph will be slanted and have some slope. The velocity time graph will always be straight lines. I'm going to repeat that. The velocity time graph will always be straight lines. They can be slanted, they can be disconnected, but they will always be straight lines. And that is because basically everything we do in this class deals with constant acceleration. Okay? So constant acceleration means the acceleration time graph is always going to be flat. So it will always be horizontal lines in some location. Okay, I hope that helped.